Okay, I got cut off in the last video because I went up to 15 minutes. Sorry about that. So the best basis theorem says that if I give you p data points in Rn, then the best basis is actually found by getting the matrix X together, right, the n by p matrix with your data, subtracting the mean, and then take the SVD, and the first k basis. So let me write down those steps. So we take the data, we get the data, we form X, we subtract the mean, and this is as a column vector, right? Then you find the SVD. Whoops, I'm writing MATLAB notation. Wow, that's bad. Find the SVD. So we take X and we compute U sigma V transpose. And these k eigenvectors are the first k columns of U. Good. So that's the best basis theorem. That's where you find the best basis. So actually you could bypass, and actually we want to bypass the covariance matrix altogether, because XX transpose can be pretty difficult to compute. And in fact, we don't need the full covariance matrix usually. So what do I mean by that? Suppose that my matrix X is 300,000 by 15. What is the covariance? What is the size of the covariance matrix? C is then 300,000 by 300,000. Okay, that's too big. That's way too big. We don't need this. Do not compute. Do not compute this. Not only is it too big for us to deal with, but it's also typically irrelevant, because you can find the values of the covariance. You could just pick off what you need, right, when you need it, and you don't really need to compute the whole thing. Good. All right. Because actually we know just about, well, we know what the eigenvectors of the covariance are by the SVD, so we don't need to compute C at all for that, right? You could also compute the lambdas, right? Do you remember that? I'll leave you to look that up in the last section there. Good. So what do you do with this once you find it, is the big question. So now I've got, I went from X1 through XP as kind of my collection of data, and I've got U1 through UK is my basis. Okay, so these are going to be in Rn. These are in Rn. And so where is my low dimensional representation? Well, I take the matrix X, right? That's n by p. And I take my matrix U, which is n by k. Right? Do you see how we're going to get our k by p matrix out of these? The coordinates of the p data points is given in matrix form by U transpose times X, right? That's k by n by p. So this is k by p. So this is p points in our k, right? That's p points in our k. Now, if you wanted to reconstruct these back in Rn, right, the reconstruction back in the higher dimensional space Rn, right, would just be U times U transpose times X, matrix X. Okay, so that's U times the coordinates. So this is the coordinates. That's k by p. This is U by k. Okay, now please be careful, because if n is very large, like we were saying, if n is like 3 million, and you just tell your computer, compute u times u transpose times x, you are going to run into trouble. Why? Order of operations, did you say that? Because the computer's going to come in here and say, I need to compute this first. And what is that? That's going to be n by n, and that's huge, usually. So you're going to run out of memory. You're going to crash your computer, uh, like I did today. But I didn't do this error, though, I must admit. But I have done it in the past. So what do you want to do instead? Be sure you have parentheses around your coordinates. In fact, it's probably easier to say, like, coords equals u transpose times x, whatever language you're using, and then say recon, the reconstruction, is u times the coordinates. And that'll guarantee that you won't get into this problem where you might run out of memory. Okay? So again, this is the coordinates here. This matrix is your low-dimensional representation. And so if we wanted to plot this, right, you would have p points plotted in RK. So typically you would take the first two, and so you would, to plot in R2, you would just take the first two columns, or the first, and in fact, you're going to have the two rows, right? You would use the 2 by p matrix of data, right? And then each of those points would be plotted in the plane. Okay, good. And sometimes this is very interesting to see. What is the low-dimensional representation of your data? Good. Now, we've talked a lot about some of the theory. What's very interesting, and what we'll talk about next, is the application of the best basis. And the idea behind the application that we're going to be doing is we're going to be looking at face space. That is, we're going to be looking at photos of faces that are fixed at m by n, right? And so these are going to be vectors in R m times n. And what we want is we want to find a set of template faces such that you can decompose your given face as the average face plus C1 times some basis vector, which actually is a face, plus C2 times another basis vector, which is a face, plus CK times another basis vector, which we can interpret as a face. Or at least we can interpret these as images. Maybe they're faces, maybe they're not. I don't know. Actually, they are kind of weird faces, but yeah. So this also emphasizes, right, that you want to mean subtract your data before you do your projection. Good. And so we're going to take this data that's in our m times n. We're going to form our matrix X. We're going to find our basis vectors. These are the eigenvectors of the covariance matrix. And so therefore we will often, or these were given the name eigenfaces. Yeah, this was actually studied quite a while ago. This is 1987 by Surovich and Kirby. Kirby would be mad if I saw me spell his name. Because Kirby was my advisor at Colorado State. And so it was kind of fun to see him talk about this. He said that never has he had such a simple paper give such a big response on the internet when things, well, I guess 87. He had lots and lots of requests for this paper, and in terms of the linear algebra, it's pretty straightforward, right? You've just seen it, right? We just showed that they didn't even use the SVD. They actually, I believe that they actually just said that, these are the eigenvectors of the covariance matrix. Excuse me. And so this is kind of the killer app of the time. Do you guys still use that phrase? Okay, I'm starting to date myself. I better stop. Okay, so the next video will actually be a computer experiment using the eigenfaces. Okay.